This is our last day on transformations, and we're going to take a look at writing transformations from graphs. So here's the sheet you're used to seeing by now with all of the transformations listed for you. Today we'll be using the parent function not to graph, but to write the equation of transformations. Our first example is given a verbal description of the transformation, so we'll look through and identify key terms. First of all, our parent function is the reciprocal function. That's the one that is 1 over x, translated 3 units left. That will go grouped with the x, and it will look like a positive. Four units up, that is outside the function, vertical shift, and vertically stretched by 2. That will go in the numerator. That 1 that is typically in the numerator will be multiplied by a 2. So that is our transformed function. Typically we identify domain and range from the graph, but we can identify that from the equation. Thinking about our critical point, -3, +4. That is where our two asymptotes meet. For the reciprocal function, that's the one that is both below and above the asymptote. So our domain will simply be x cannot equal -3, and our range would be y cannot equal 4. For you visual people, as a quick reminder, this is what the graph would look like to help you connect it to the domain and range. -3, 4 would be where our two asymptotes meet. There was no reflection, so this one would be in the first and third quadrants around our asymptotes. Another verbal description, this time we have the greatest integer function. That is also our step function, so there's our parent. We have a vertical reflection that will go on the outside, and that's multiplication by a negative. Horizontally stretched by 2. That goes inside with the x, and it's not normal. So it might look like a 2 outside, but that means we're multiplying by 1/2 on the inside. Translated 1 unit right. We need to put this in parentheses. The translation and the stretch or compression need to be separated from one another. Right would look like a +1 if it were normal, but it's inside the asylum, so it's a -1. And finally, 4 units down, so that is on the outside and it's normal. Domain and range on this one. The rounding function has a domain of all real numbers that does not change under any type of transformation. For the range, what we need to worry about is any vertical stretch. We have a vertical reflection, but that does not impact the range. So our output would still be integers. And we'll take a look at writing transformations from a graph. First of all, we'll identify our parent function. This, of course, is a parabola, or the x² function. We're given a few points for the transformation, and we can use those to figure out what the transformation is. One way to try and identify our transformation is to think about the parent function. What parent function values do we get, and how did they change on the graph? Because our graph is only off to the right of the critical point, I'm going to start with the critical point and do 2 points to the right of that for our parent function as well. Squaring each of these values, I would get 0, 1, and 4. Taking a look at our graph, the y values are 0, 1, and 4. Nothing changed for our y value. We have no vertical change to our graph. But we do have new x values. Our x values are 2, 3, and 4. So let's take a look at what happened from the parent function x values to our transformed x values. For 0 to 2, we added 2, and that pattern holds from 1 to 3 and 2 to 4 as well. So So our transformed function was a shift to the right 2, which means it's grouped with the x and it's not normal. Domain. The domain of our parent function is all real numbers. That does not change under any transformation. And for our range from the graph, we can see that our y values are greater than or equal to 0. Our final example, we can tell that our parent function is the absolute value because it's in a V shape. The equation for this one is a little bit challenging because as we look at this graph, there aren't any very nice coordinates that we can use to write our equation like there was on the last one. I'm just going to grab this point here, 1/2, 0. The reason I know it's 1/2 and not 1 is because this point here was identified to me as 0, 1. I'm going to use just those 2 points in my t-chart because I can tell that this graph was stretched or compressed. So unless I tried to use this point here at the same rate, any other points I choose would be off from the pattern. All right, my 2 parent function values, since I'm starting with the critical point and 1 point off to the right would be 0, 1. The parent would leave them alone, the absolute value function. My 2 x values are 0 and 1/2, and my y values are 1, 0. Thinking about what changed, from 0 to 0, nothing changed for my x value, but 1 went to 1/2. So it looks to me like we have a horizontal compression by 1/2. Of course, that would not change the 0 when we multiply. For my y values, I went from 0 to 1, which looks like I'm going up 1, but then 1 went to 0. The other thing I noticed from the graph is we have a vertical reflection. Our graph is opening down instead of up. So I know that my parent function values were multiplied by a negative. And from the critical point being at 0, 1, I also know that we have a vertical shift up 1. So let's see if that works for this second parent function value. If I multiply 1 by a negative for the vertical reflection, I will get -1, plus 1 for the shift would give me 0. Using those 3 pieces of information, I can get my transformed function written. The vertical reflection will be on the outside of the absolute value. The horizontal compression will turn into a reciprocal of 2x, and the vertical shift is outside the absolute value as well. Taking a look at our domain and range, for the absolute value, domain is all real numbers. That does not change under any transformation. For our range, the vertical reflection puts the graph below the y value of our critical point, and in our case, the critical point is 1. So our range is y is less than or equal to 1.